So in this video, I'll discuss another concept or phenomenon that supports the idea that light is quantized or it exists in discrete forms or in discrete packets. Okay? So this is the existence of the so-called atomic line spectrum. So according to classical physics, an electron can have any value of its momentum. So speaking of momentum, meron tayong dalawang types ng momentum. We have the linear momentum for the linear motion. So kapag linear momentum, P is equal to the mass of the particle times its velocity as it moves from one point to another in a linear fashion. Meron din tayong tinatawag na circular motion. So kapag meron tayong specific center, tapos meron tayong particle na nagre-revolve around that center, yung angular momentum naman ng particle na nagre-revolve can be calculated using this equation. So the angular momentum is equal to the mass of the particle, its velocity as it revolves around this center, tapos meron din tayong r. So r is the distance between the revolving particle and the center. Okay? So that's angular momentum. So when we say momentum in this case, since ang pinag-uusapan natin dito ay yung mga electrons dun sa mga atoms, so yung electrons natin nagre-revolve siya around the center of your atom. So ibig sabihin, we are talking about angular momentum. Okay? So this momentum is the angular momentum. So according to classical physics, electrons can have any values of the angular momentum kasi pwede naman tayo magkaroon ng any value ng velocity. Tulad din dito sa linear momentum. Okay? So therefore, it can absorb light at any wavelength. Kasi if you supply any amount of energy, it will increase the angular momentum of your electron at any degree. Okay? So yun yung classical physics na concept. So, meron tayong dalawang klase ng spectra. Meron tayong emission, okay? So, kapag emission, it came purely from the emission of your electron. Kapag naman absorption, so pinapass natin yung incident light doon sa electron tapos titingnan natin kung ano yung mga wavelengths na naa-absorb niya. Okay? So, dito muna tayo sa emission. So, ang gagawin muna natin, i-heat natin yung atom. So, we will introduce energy dun sa electrons para magkaroon siya ng tinatawag na excited state. Tapos hahayaan nating mag-cool down or bumalik sa ground state yung ating electron. Okay? So pagka bumalik na siya dun sa ground state niya, mag-emit siya ng radiation. So this radiation has a specific wavelength. So ang gagawin natin doon, i-refract natin siya using a prism. So prisms, okay, refract white light para mas-segregate mo yung wavelengths. So since we have a lot of electrons doon sa ating system, okay, and marami din tayo kasing atoms doon. So each electron has a different absorption na ng ating incident energy. Okay? So kung iba-iba yung na-absorb nilang energy, iba-iba rin yung i-emit nilang emission wavelengths. Okay? So since we can have any possible value of the angular momentum possible, so pwede nating ma-absorb lahat ng light or lahat ng energy o pwede tayong mag-emit ng any wavelength of light. Okay? After the de-excitation. So kapag balik niya sa ground state, pwede siya mag-emit ng light in the blue region, pwede siya mag-emit ng light from the green, from the red, etc. Okay? Depende dun sa energy na inabsorb niya. So that's according to classical physics. So ibig sabihin, okay, kapag kinuha mo yung emission ng lahat ng yon, pwede tayong magkaroon ng continuous na spectrum. So ano ibig sabihin nun? If your spectrum is at the visible region, wala kang makikitang gaps dun sa ating spectrum. Okay? So continuous siya. Parang rainbow. Ibig sabihin lang yan, pwede siya mag-emit ng lahat ng possible wavelengths inside this specific spectrum. Okay? So, dito naman sa absorption spectrum, okay, i-interact natin yung electron with specific white light. So, ibig sabihin yung white light na to, meron siyang iba't ibang wavelengths of radiation na nandyan. Okay? Tapos, pag inabsorb siya nung ating electron, okay, titingnan natin ngayon kung ano yung hindi niya ma-absorb. Okay? So, yung hindi niya ma-absorb, yun yung dapat nalalabas dito. Pero nakikita natin dito na walang color. Wala tayong nakikitang lines. So, ibig sabihin, lahat ng wavelengths na pumasok sa electron, na-absorb niya lahat. Okay? So, wala tayong makikita sa absorption spectrum kasi na-absorb niya lahat. That is according to classical physics. Yun yung kanilang parang prediction. However, experimental data shows a different result. So, kapag pinerform natin yung experiment to determine the emission spectrum of your electron, okay? So this is for hydrogen, for example, okay? Makikita natin na yung emission spectrum ay lines lang. So ibig sabihin hindi siya nag-absorb at all wavelengths or hindi siya nag-emit pala at all wavelengths. Makikita natin na ito lang yung mga in-emit niyang wavelengths. Okay? So, hindi siya continuous. It's just a line spectrum. So, it's a spectrum made up of separate, distinct lines. Okay? So, yan yung line spectrum for the emission spectrum of your hydrogen, for example, or your electron ng inyong hydrogen atom. So, dito naman, okay, kapag ka nag-pass through ka ng light dun sa inyong electron, okay, hindi niya ma-absorb lahat kasi lalabas most nung color dun sa absorption spectrum. Yung mga nakikita nyong color dyan, yan yung mga light wavelengths na hindi niya na-absorb. Yung mga gaps, yun yung mga light na na-absorb niya. So makikita nyo, corresponding yung ating emission and absorption spectrum. Kung ano lang yung light na na-absorb niya, okay, yun lang din yung light na i-emit. Okay? So that's for the energy of your um, electrons. Distinct lang yung nagiging angular momentum change ng ating electrons. So, ibig sabihin, yung light natin, okay, hindi siya continuous. Nasusupply siya dun sa electrons in distinct packets, like a particle. Okay? So, that is for the atomic line spectrum. Yan yung kanilang observation. So, paano nila to in-interpret? So, Niels Bohr suggested that these lines are caused by discrete values of angular momentum. So, tama naman. Okay? Dapat discrete ang values ng angular momentum kasi hindi tayo magkakaroon ng mga ganitong lines kung continuous yung ating angular momentum values. So, ibig sabihin yung electron mo, hindi siya pwede magkaroon ng kahit anong value ng angular momentum. Distinct values lang ang pwede. Okay? So, ngayon, Niels Bohr suggested an orbital model of the electron or the atom. So, ano yung orbital model? So, meron kang center at meron kang mga orbits na tinatawag. So, dun lang sa mga orbits na yan, pwedeng malocate yung mga electrons na to. Okay? Hindi tayo pwedeng magkaroon ng electron in between those orbits kasi those orbits represent angular momentum. Okay? So, yung mga angular momentum na wala dun sa lines, those are forbidden angular momentums. Hindi sila yung angular momentum na napopossess ng electron. Hindi po pwedeng magkaroon, for example, na angular momentum na n is equal to 1.5. So, this is not allowable according to the data. Okay? So, yan yung model ni Niels Bohr. Distinct lang yung pwedeng maging mga posisyon ng electron with respect to the atom. Okay? So, ang tawag dyan ay orbitals. So, ang dinidiscuss lang natin dito ngayon ay yung energy levels. Hindi pa natin dinidiscuss yung shape tsaka yung orientation. So, energy pa lang. So, according to Niels Bohr, okay, the electron can only have certain values of angular momentum. So, that is what happened here. So, kapag ka nag-a-absorb ng light yung iyong electron, napopromote siya dun sa susunod na energy level na tinatawag or angular momentum. So, tumataas yung angular momentum niya pero only at a certain degree. So, that's during absorption. So, kapag ka nag-absorb siya ng specific wavelength ng light. Kapag yung wavelength ng light na yun ay hindi corresponding dun sa distance between the two angular momenta or any other angular momenta na nag-exist dun sa ating atom, hindi niya yun i-absorb kasi that's forbidden. Okay? Magpo-produce siya ng angular momentum na hindi included dun sa mga distinct lines na sinasabi ni Niels Bohr. Okay? Dapat kung mag-absorb ka, allowable dapat yung energy para mag-change ka sa allowable angular momentum. Okay? So, meron tayong mga angular momentums na hindi allowed. Yun yung point ni Niels Bohr. Okay? Kapag naman nag-emit ka from the excited state, okay, bumabalik ka lang dun sa initial state mo or sa tinatawag nating ground state. Okay? So, ganyan yung electronic structure of the atom according to Niels Bohr. So, ito yung mga allowable transitions. So, as long as your transitions are corresponding to distinct values of n, okay? So, n equals 1, 2, 3, 4, 5, 6. As long as nasa lines yung mga electron mo after each energy emission or absorption, allowable yung transition na yun. Yun yung sinasabi ni Niels Bohr dito sa model niya. Okay? So, ganyan ka-quantized yung light. Meron siyang mga sinusunod na integral values. Okay? So, that's how Niels Bohr interpreted the orbitals or the energy levels of your atom. Okay? So, Rydberg, which is a spectroscopist, okay? So, spectroscopists study spectroscopy. So, spectroscopy is the study of light and its interactions with matter. So, he derived an equation based on the data that can be used to predict the frequencies of emission lines of hydrogen. So, hydrogen lang muna yung inaral niya kasi yung mga ibang many electron atoms like helium, lithium, beryllium, marami silang electrons na pwedeng mag-interfere doon sa energy ng electron na ino-observe. So kapag kasi may iba kang electrons, baka yung mga energy levels, okay, hindi natin accurately malocate. So for hydrogen, he derived this equation. So the wave number of the line, okay, of a specific line is equal to the Rydberg's constant times the quantity 1 over Ni squared, where Ni is the ground state integer. So this is the energy level of the level that has the lower angular momentum. So that's minus 1 over Nf squared. Ito naman yung energy level ng level na may mas mataas na angular momentum. So if you have a transition from Ni to Nf, so ibig sabihin from lower to higher angular momentum, so yung angular momentums dito ay represented na ng energy levels. So yung energy levels ay integers. Okay? So they are 1, 2, 3, 4, etc. So for example, you have a transition from 1 to 2, so that's n equals 1 to n equals 2. Pwede mong ma-predict yung kanyang wave number or yung line associated with that particular transition. Okay? So, yan yung ginamit na equation ni Rydberg para ma-predict yung lines ng hydrogen. Depending on the ground state, kasi hindi naman palaging 1 yung ating ground state. Pwedeng ang ground state natin ay 2 or 3. Depende dun sa ating experiment. Okay? So, mape-predict mo dito yung mga lines or yung mga emission lines ng inyong hydrogen atom. Okay? So, maraming mga spectroscopists yung nag-study ng mga lines ng hydrogen. So, kinuha nila yung mga lines, pinredict nila. Okay? So, discuss muna natin dito yung Lyman series. So, yung Lyman series, ito yung pinaka-basic kasi yung ground state niya ay n equals 1. So, ang ginawa lang ni Lyman dito ay kinuha niya lahat ng wave numbers ng mga transitions from n equals 1. So, ano yung mga transitions na yun? So, kinuha niya yung energy ng transition from n equals 1 to n equals 2. So, 1 to 3, 1 to 4, and 1 to 5. Okay? So, yung mga transitions na yan from lower angular momentum, which is n equals 1, to the energy levels na may mas mataas na angular momentum. Okay? So, ginamit niya yung equation. Okay? Actually, kinuha niya muna yung value. Tapos, ang ginawa niya, finit niya doon or tinignan niya kung mag-agree dito sa Rydberg Equation. Okay? Actually, yung Rydberg Equation yung pinakahuling na-establish kasi kinolect nila tong lahat ng data na to. Tapos nakita nila yung relationship. Okay? So, Lyman was the first one to explore the lines of hydrogen. Okay? So, using the Rydberg equation, we can predict the frequencies of those lines. So, for example, we have the wave number of the transition from n equals 1 to n equals 2. So, using the equation, okay, r times 1 over 1 squared. So, this is actually c sub r. So, minsan kasi ang ginagamit nila ay r. So, pwedeng r or c sub r, yung ating Rydberg constant. So using this formula, makukuha mo yung line associated with the transition from n equals 1 to n equals 2. So that's 82258.18 reciprocal centimeters. So to be able to convert, okay, the wave number to wavelength, alam nyo naman ang gagawin. So ang gagawin nyo muna, kukunin nyo muna yung reciprocal ng inyong wave number. So makukuha nyo ay yung centimeters. Iko-convert nyo siya sa meters. Tapos pag nakuha nyo na yung meters, iko-convert nyo naman siya sa nanometers para makuha nyo yung value na to. So 82258.18 reciprocal centimeters is equivalent to a wavelength of 121.57 nanometers. So yung transition naman from 1 to 3, yung wave number niya ay 97491.17 reciprocal centimeters. That's the transition from n equals 1 to n equals 3. So nilagpasan na niya yung n equals 2. So mas mataas na change in the angular momentum ito. So, syempre, yung kanyang wavelength ay mas maliit kasi mas mataas yung energy nito. So, that's 102.57 nanometers. So, for the transition from n equals 1 to n equals 4, makukuha natin ay 102,822.72 reciprocal centimeters. That's equivalent to 97.25 nanometer wavelength. So, mas maliit yung wavelength kasi mas mataas na yung wave number. So, finally, for the transition from n equals 1 to n equals 5, we'll get 105,290.47 reciprocal centimeters or 94.928 nanometers in terms of wavelength. Okay? So ito na agad lahat yung inyong mga wavelengths, okay? Associated with the lines of the Lyman series. So makikita nyo yung mga wavelengths na to, it corresponds to the ultraviolet region. This is less than 400 nanometers. So nasa ultraviolet region na to, matataas na energy na wavelengths to. Okay? So, there it's so yan yung ating ultraviolet region lines. So, yung Lyman series natin ay nasa ultraviolet region. Okay? So, next we have the Balmer series. So, yung Balmer series, okay, nag-start siya sa n equals 2 na ground state. So, ano ibig sabihin nun? Yung mga transitions natin ay 2 to 3, 2 to 4, 2 to 5, 2 to 6, etc. Okay? So, substituting those energy levels to the Rydberg equation. Okay? So, for example, yung ating transition from n equals 2 to n equals 3, substitute lang natin. So, from 2 to 3, ito yung Rydberg constant, makukuha natin ay 15,232.996 reciprocal centimeters. That's equivalent to 656.47 nanometers. So, mapapansin nyo, it's within the 400 to 700 nanometers. So, visible to. This is actually the red color or it's near the red and the orange boundary. Okay? So, kapag naman 2 to 4, okay, so makikita nyo, ito yung value, 20,564.545. That is equivalent to 486.27 nanometers. Okay? So, for the transition from n equals 2 to n equals 5, we will get 23,032.29 reciprocal centimeters. That's equivalent to 434.17 nanometers. So, malapit na siya dito sa violet na region ng ating visible light. So, from 2 to 6, we have 24,372.79 cm negative 1. We also have this 410.29 nanometer as the equivalent wavelength for this wave number. Okay? So makikita nyo itong mga wavelengths na to ay corresponding to the visible region. It's between the 400 to 700 nanometers. So as the transitions increase in the change, okay, so kapag nag-i-increase yung amount ng transition, halimbawa from n equals 2 to 3, okay, tapos pagka change mo na siya from n equals 2 to 4, okay, bumababa yung wavelength. So papunta siya sa blue. Okay, from red to blue. So, all these wavelengths are within the visible region. So, makikita nyo tong mga lines na to as colors. Okay? So, this is my discussion on the line spectrum of hydrogen. So, sa susunod na discussions, I'll go further into the calculations. Tapos, meron akong sample problems for other line spectra. Kasi marami tayong line spectra. Meron pa tayong Paschen series. That's at the ground state of n equals 3. Okay? So, magagamit nyo yung Rydberg equation actually to determine any wave numbers for any distinct transitions. Okay? For the hydrogen atom. Okay? So, tutuloy ko na lang tong discussion sa susunod na video. So, see you next video.